Good morning. In this session, I would like to demonstrate energy balance calculations involving a combustion reaction. For example, you can see air at these conditions is mixed with 3000 kg per hour of methane at 15 degrees centigrade and 1000 kilopascals. The mixture is compressed and then fed to an adiabatic combustor. So 100% conversion of methane is happening to these products. So the air flow rate is designed to give a temperature of 1400 degrees centigrade at the exit of the combustor. The hot gas leaving the combustor is expanded in the turbine. So shaft work produced by the turbine is used to power the compressor. So you are required to identify the net rate of power production. So let us see how to simulate this problem using Aspen. So first of all, define all the components, especially when you are using air for combustion. Though air is available as a component in Aspen because air itself is not going to participate in the stoichiometric chemical reaction. Better to identify that as a mixture of oxygen and nitrogen. Then we have methane and the combustion products. Air, methane, and the combustion products are CO2 and water. So these are all the components that we are going to make use in this simulation. So go to the next step, use a property method, go to the next step and go to simulation environment. Now the fuel is mixed with air and then compressed followed by the adiabatic combustor. Remember, we don't have any details about the kinetics, so we have to make use of stoichiometric reactor model. And after this, we are trying to make use of a turbine. So both compressor and turbine, the model is the same, but while defining, you have to designate whether you are using it for calculating a compressor or maybe a turbine. We will see that. Okay. Now let me connect the input and output streams. So let us say this is the methane or fuel, air, entering into a compressor, wherein it is compressed to about 2900 kilopascals. And the exit of the combustor is sent into a turbine and you are using the product. Did I miss anything from the problem statement? Right. So you can go back and try to define the process. So air, this is S1. Okay, before going into that, let me name some of these for convenience. Let us say this is the methane. In general, call it as maybe fuel. And this is air. We have some requirement with respect to this temperature. So let me also rename this stream combustion out. So now let us go into the next step. So we are defining the fuel. We know all the details, 15 degrees centigrade, so 1000 kilopascals. And it is entering at the rate of 3000 kg per hour. Methane. Next. So this is with respect to air, which is also entering at 15 degrees centigrade and 1000 kilopascals. And you know the composition of air for all practical purposes is taken as 21% oxygen and 79% nitrogen. Right. But what about the flow rate? See, of course, we need to find out the air flow rate that is going to give us the required temperature of 1400 degrees centigrade at this outlet. So to start with, we may have to assume the flow rate. For example, 3000 kg per hour roughly is about 200 kilomoles of methane. So 200 kilomoles of methane require 400 kilomoles of oxygen. So if 400 kilomoles of oxygen is required, we may require roughly 5 times. So let me assume the flow rate of A as 2000. It's a rough estimate. Anyway, we may have to redesignate this, recalculate this based on the requirement. So we have defined the A stream. Next. This is 15, 2000. This is not 3000. We are defining A, so this is 0.21 mole fraction, 0.79. So we have taken care of the A. Next, we have to talk about the fuel. So which is 15 degrees centigrade, 1000 kilopascals, and the mole flow, mass flow is of methane is 3000 kg per hour. This is of course meters. So we have defined the fuel. Now go to the next step. Next. Now we are asked to calculate the compressor, define the compressor, choose the type of compressor. Discharge pressure is 2900 kilopascals as specified in the problem statement. We have specified the compressor. Then we are talking about the last unit, which is actually a turbine. So take it as a turbine, isentropic. What is the discharge pressure? As you know, the lower the pressure, the higher would be the power output. But one of the problems that we normally encounter when you expand gases in a turbine is there is a possibility for condensation of vapor. For example, water vapor might get condensed. Yes, small droplets of water are not permissible in the case of turbine because they will be eroding the turbine blades quite quickly. Anyway, let me maintain slightly higher pressure than the atmosphere and also say that I don't want to do vapor liquid calculations, we only deal with vapor. You can check up if you put vapor liquid, there may be a possibility of some vapor to get condensed, so that may be reported. Okay. Having defined the turbine, now we need to talk about the stoichiometric reactor. So this is operating at, again, we are given that it is an adiabatic combustor, so duty is 0 and the pressure drop is 0 because the input is at 2900 kilopascals. The reaction also will be occurring at the same. So next, the reactions new. So you know methane coefficient is 1 reacting with oxygen. So you require for every mole of methane 2 moles of oxygen. And the combustion products are CO2, which is 1, water also 2. So fractional conversion is 100% with respect to methane because this is the limiting reactant in this problem. So we have defined this and all the required input is complete. So we should be in a position to run the problem. Now you can see the stream summary, but before going into the other results, we wanted to ensure what is happening at the end of the reactor. Now you can see the air flow rate should be designed such that we should get 1400 degrees centigrade at the exit of the combustion. But what we have is 1976. Now just to check up whether all the methane is converted or not, you can see out of the 420 moles of oxygen that is supplied, still there is some excess oxygen. So all the methane is converted into products. But the issue here is whether how much air is to be supplied in order to get the required temperature of 1400 degrees centigrade at the exit of the combustor. So in order to solve this problem, now we would like to use a flow sheeting analysis, go to design spec, say new. So what is the requirement? We wanted to get some target temperature of 1400 degrees centigrade at the exit of the combustor. So this is a stream variable, and the stream is combustor out, and the variable is temperature. What is our requirement? this target temperature should be 1400 degrees centigrade and with some tolerance. What is that we would like to vary? We wanted to find out the air flow rate because we started with an initial approximation of about 2000 kilovolts per hour. So this is going to be a stream variable. Stream is air, variable is mole flow. So we started with 2000. Even this 2000 gave us something like 1900 degrees centigrade temperature. So this should be higher. Let me assume that the solution is lying somewhere between 2000 to 10,000. You can go and see. So we started with air flow rate of 2000 and calculated the outlet temperature. Compare this with 1400. If it is not met, if the requirement is not met, then you adjust the air flow rate. From 2000, you try to increase such that the temperature here is equal to 1400. Right. Now let us run this problem. Now you can see the solver or the design spec is the measured variable is here, the manipulated variable is here. So all the blocks within these two will be forming an iterative loop. So block B1, B2, B3 are iteratively calculated till you reach a convergent solution. Once you reach a convergent solution, then B4 is calculated. So we were able to get to a convergent solution after 7 iterations. The method usually is secant, like what you have seen in even earlier problems. Now let us look at the results. When we used an air flow rate of 2000 kilomoles per hour, we got a temperature of 1976. But when we increased it to about 30 to 38, we were able to get to the required temperature. So this is one issue in this problem. Now let us look at the other issues. What is the amount of power produced in the turbine? Remember, the power produced in the turbine is dependent on the exit pressure. So we said it is 2 bar, okay? So an amount of network, why is it negative? Because the turbine will be delivering work. So as per thermodynamic notation, this is an amount of work that you will be able to get from the turbine, which is equal to about 19,221. Now, in this process of generating energy, we may have to spend some energy in the compressor. So this is about 3,926. This has to be inputted into the compressor because it is positive. So 19,000 odd amount of energy is obtained from the turbine. Part of that is utilized by the compressor. So the difference between them should be giving you the net work obtained. So minus 19,000 something, that is here, minus 19,221 plus 3,926.37 will indicate the net amount of work generated by this process. Of course, in the process, you are combusting a fuel like methane. Now, in order to do this problem, there are other alternatives. In fact, you can just concentrate. Till now, we have not seen this type of problem. So, along with material streams, you also have heat and work streams. So, I'll be selecting this work stream. So, the work that is produced from the turbine is utilized, is sent into the compressor. Okay. So, when you send this work, do you think all the work that is produced by the turbine is it utilized by the compressor? No. So it has to take whatever work that may be required by the compressor, and the remaining work is going to represent the net amount of work that is produced by the process. In fact, we were already able to calculate this, but the advantage of using heat and work streams are energy delivered from one unit can be utilized in another unit like this by using either heat or work streams. So this will help you to maintain heat integration, work integration and so on. So with this modification, let me run the problem. Now there is not much change, but you can see from the flow sheet, if you click on this work, now it will tell you the difference between 19,000 something minus 19,000 plus about 3,900. So this is the net amount of work that you are able to generate in this process by burning the fuel. Again, if you are interested, in order to deliver this work, you can calculate what is the amount of percent excess air that you have used by using your conventional calculations. So the new thing that you will be able to see from this process, from this example is, you will be able to integrate heat or work by using heat streams or work streams, right? That is a new concept that you will be able to learn from this demonstration. So with this comment, I would like to close my session.